So first up, again, is the dynamic traffic assignment. We're going to continue on from our session last time and take a look here at part 2. So last time on ToolTips, we took a look at the different network objects associated with DTA. So we looked at nodes and creating zones and parking lots. And today we're going to look at all of the different parameter settings. And then next time we'll take a look at actually running the model, looking at results, and then doing some fine tuning. So just a quick recap about dynamic traffic assignment. So this is going to be different from the vehicles that are applied using static routes and vehicle inputs. In this case, vehicles will enter the network based on an origin destination matrix. And any vehicles that enter the network will be able to choose different paths. And this will be an iterative process since they are going to be making a choice. So multiple simulations will need to be completed. And as a part of DTA, once you have your network built, at the very beginning, there won't be any paths or any assessments made by the vehicles, since no one has entered the network yet. So the very first simulation will be run. And in this case, since vehicles don't know anything about the traffic conditions or have any information about travel times, they're just going to base their decision on distance. And so they will all take the shortest path. Once that simulation has been completed, that you'll be given your first set of paths and then the costs associated with those paths. And so these costs will include things like the travel times for the path, the distance of the path, and then also some of the financial costs. These will then get put into the next simulation run. And that simulation run will use those paths and costs. Additional paths will then be generated along with a new set of costs. That will get fed back into the simulation so that the vehicles can update their travel times. And then this process will continue until you reach a solution that has been converged upon. So this is kind of the process for all of the different parameter setups that we're going to go through today. So we're going to take a look at all of the different files that are involved, how vehicles are going to come up with the cost definition for all of these different paths, some options for actually searching for the path and then making that path choice, and then looking at some of the criteria that we can set up to determine when a solution has converged. And then finally, we're going to look at this last option here for route guidance. So all of the parameters for dynamic assignment are in the traffic menu. So you'll just go to traffic and then dynamic assignment and then parameters. And that will open up this window here on the right. And so we're just going to kind of go through today and talk about each of these different tabs. So the first one up is going to be the file settings. So this is where you can set up what matrices you want to pull in. So you can have different matrices for different vehicle compositions. Perhaps you have one for private vehicles or maybe a different one for heavy trucks. And then you can also set these matrices to pull in different time periods. So if you wanted to maybe model different times of day, you can set those up and then use all of these matrices here. There is also an option below that matrix box where you can scale that volume. And so this will just be the initial scaling just to reduce the demand initially. And this is to help avoid any initial congestion that occurs just due to the fact that not many paths have been found in the network yet. So the demand can be scaled down, and then over different iterations of the simulation, that can be scaled up based on a setting in simulation parameters. And once that full demand volume has been reached, then all of the vehicles entered in the matrix will enter onto the network and will be continued to be used for all of the future runs. And then the second half here, at the top, we can set up the evaluation interval to determine when those costs and paths are going to be calculated. And then directly below that, we have the location of where these cost and path files get stored. And so by default, these will just be stored in the same directory as the IMPX file. And these are going to be another external file, so you'll see them, this .bew and .weg extension. You'll see those show up, and these will just be some external files kind of shown here below. And in order to store these files, you'll just need to check Store Costs and Store Paths down here at the bottom. And once the dynamic assignment process has been completed, you can uncheck those so that vehicles will just use the information that was last stored in these files. All right, so the next option here we're going to take a look at is how the cost is going to get defined for the path. So in order for the vehicles to choose what path to take, each of the paths will have a cost associated with them. And this cost is not just the financial cost, but it also includes travel time information, the distance of the path, and then it also includes another surcharge that is defined by the user if you wanted to kind of apply an additional factor to a particular link. So each of these contains a coefficient here, so like alpha and beta and gamma. And these coefficients are based on different vehicle types. So if you go to the vehicle types window, in here, this cost coefficients button is where you can set up kind of the weight that you want to use as part of the cost calculation. So this would be used if maybe you had maybe a private vehicle that kind of wants to avoid those toll roads and maybe doesn't want to take some of those financially higher paths. Whereas maybe a delivery truck, they're going to put more emphasis on travel time. So they maybe will have kind of a higher weight towards that travel time. Now, as part of this cost equation, the travel distance, the financial cost, and the surcharges, those will all be set up based on how that network has been built and defined. But the travel time is going to be something that's going to be constantly updated as the simulation is run so that vehicles can kind of react to the traffic conditions. So as part of the cost tab, this kind of covers all of the different information associated with the travel times. So the very first option here is picking the time interval to use as part of this path search. So you can either look at the same time interval, but in the previous simulation. So in this case, if we're looking at 1800 seconds, that would be compared to the last run. Or you can also set that to just look at the last time interval in the current simulation. So it'll just kind of point back and use that previous iteration. And then the middle section here has to do with the cost calculation that's used. So you can either choose to sum up all of the travel times along an edge, and this could include vehicles using different paths. So for example, if we're looking at vehicles traveling from A to B, this middle section here that's 20 minutes also is going to include vehicles traveling from A to C and from D to B and C. So as part of that sum of edge travel times, you may end up getting any sort of vehicle that travels over that edge will be included. The other option is to just use the measured path travel times. And so this will be the travel times for vehicles that are only using that entire path. So that would only be vehicles traveling from A to B. And this might differ. So in this case, for this example, maybe the vehicles making that direct path only take 35 minutes instead of 40. And maybe this would happen because vehicles maybe make different lane change choices. Maybe vehicles going from A to B know far in advance they need to kind of stay on the right-hand side, so they wouldn't have to spend as much time making lane changes, and they already know where they're going, things like that. So just a couple of different options here that you can select to determine how those travel times will get calculated. And then for each of the iterations, the simulation is going to look at travel times for all of the past iterations, not just the last one. So in this case, we can also look at some different smoothing methods to determine the influence of these other iterations. So the first option here, this exponential smoothing, in this case, you can just set a factor to apply. And this essentially says the more distant iterations are going to have less influence. So in this case, with an alpha of 0.5, you can see that over each iteration, kind of the weight of that iteration is going to go down by half. So this is just a way to say that to determine how much influence kind of those further iterations have on the current iteration. And then the other option here is the method of successive averages. And so in this case, the current iteration will have the same weight as the previous iteration. And essentially, this ends up resulting in an average from all of the simulations. All right, so now that we have our cost defined, now we can take a look at the different options available for searching for paths. So first up, we can choose an option to search for new paths that will be added to the existing path set before vehicles make their selection. The second option is to search for alternative paths, which may help vehicles find maybe some of those higher cost paths rather than maybe the lower cost paths that have shorter distances and travel times. And then the final option here is to allow paths to be kept in the list that for OD pairs that don't have any volume. So this might occur if you have an OD pair that has a really low volume set in the matrix, something less than 1. In that case, for some simulations, one vehicle may get placed on the network. In other cases, maybe no vehicles get placed on the network due to rounding. So in this case, if there's a chance of a vehicle entering the network, you might still want to keep those paths around so that that vehicle will have a place to go. And then we can also decide how vehicles, or when vehicles choose their path. So they can either choose it at the very beginning at their origin parking lot and know where they're going right from their origin. Or you can also choose to decide repeatedly, in which case the vehicles will decide as they approach each node. So once they're getting close to a node, they'll take a look at all of the different turns and then make a decision about which turn to take. And then once the vehicle completes that path will get saved in that path list. All right, so now we kind of have our group of paths and the costs associated with them. So now we're going to take a look at how vehicles make that path choice. So in this case, vehicles kind of have two decisions to make. The first one is which destination parking lot to go to. So in this case, you'll see here we've got vehicles traveling from Zone 1 to Zone 2. And in this case, Zone 2 is tied to two different parking lots in different locations. So the very first decision vehicles need to make is which one of the parking lots they need to go to. And then vehicles will need to decide which path to take in order to get to that parking lot. So first we'll take a look at that parking lot selection process. So this is based off of a utility function. So this will include things like the price to park, the attraction factor that's set up by the user, the distance from the parking lot to the final destination zone that that trip would go to, and then also the travel cost associated from the vehicle's current position to the parking lot with the lowest cost. So this could be something like maybe if you are trying to go to a parking lot that's closer to your destination, what does that cost look like compared to maybe another parking lot with a higher cost? And then finally, it'll also look at the amount of availability or free space in that parking lot. And then each of these also have a coefficient associated with them. And these are also set up within the vehicle type. And in this case, you'll just look at that destination parking lot selection. And this is where you can set up the different values for those coefficients. So then this utility function will get applied in a logit model. And so this is where that probability comes in of choosing one of those particular parking lot destinations. And so if we go back to our parameter window here, kind of this first part up here at the top will allow you to enter in two different options here. The first is going to be the scaling factor. And so this is going to be that K value here in our probability equation. And so this really just determines the sensitivity of the function. And essentially, higher values of K mean that vehicles will prefer parking lots that have a high utility. So if we take a look at this graph over here on the right-hand side, you'll see the green line here has a utility of 20. So this will be our highest utility function, while the other two have a little bit lower utility. So as the value of K increases, you'll see the probability of choosing one of these functions will change. So if you have a very low value of K, the probability of choosing these paths is going to be pretty similar. However, as K increases, you can see it starts to really going to start to prefer that high utility parking lot. And so based on the way, based on these functions, you also have to set a lower limit value. And essentially, this just allows a chance for these lower utility functions to be selected. If that lower limit was set to 0 and the K value is kind of set greater than 1, you can see down here that that probability is really, really low. So this lower limit just kind of gives the vehicles a chance to still be able to select those other parking lots even with a higher K value. All right, and now we're kind of going to switch over and take a look at the path selection. So before we go into the path selection, we can choose some options for vehicles to avoid some longer detours. So in this case, you can set a factor, which by default is 2.5. So vehicles will avoid any of the paths that they consider a detour based on this factor. So in this case, it's going to be based on the path length. So in this case, if this other path is maybe 3 times longer than the straightaway path here, vehicles would choose to avoid that and would just take that original path. You can also have vehicles reject paths that are considered to be too expensive and have too high of a cost value. And you can also limit the number of paths per origin-destination relation. All right, and now moving down into the path choice model section. So the first option here is just to use the old volume from the last iteration. And so this is what's going to pull in those saved values from that path file. And this will also result in no new path searching. So this would be an option you'd want to select too once you have your dynamic assignment process completed and a converged result. And that way you can just have the vehicles look back and just use those probabilities that are saved in that path file. All right, and then moving on to kind of the two different assignment methods. Here we have, first one is the stochastic assignment, or Kirchhoff. And so this is going to use a utility function, which is going to be the inverse of the cost. And if you recall from a few slides ago, here's that cost function. So again, this is going to look at the travel time on the path, the distance, any financial toll charges, and any user-defined surcharges. So using this cost function, we'll create that utility function. And then that utility function will get applied in the path probability function in order for vehicles to be able to choose what path to take. And so in this case, you can select the exponent here, which is this little k. And so higher values of k are going to put more weight on kind of that best route that's going to have a higher utility, which in this case would be a lower cost. So here in the chart, if you can see here, the utility for the blue line is 4. So this is going to be our highest utility function, whereas the green and red will be the lower ones. And you can see as the exponent increases, we'll just have more of a probability of choosing this best path. Here's just a small example of 1,000 vehicles traveling between A and B. There are two different paths here. The first one, the green one, has a cost of 25, and then the blue path has a cost of 50. So based on the Kirchhoff exponent set here, you can see how the kind of the distribution of vehicles is. So as that exponent increases, you can see that more and more vehicles will end up taking path number 1 because it has a lower cost and therefore a higher utility. And then the second option here for assignment is the equilibrium assignment. And so this is going to just take the demand and redistribute it proportionally based on the cost values. So if you take a look at the this green chart here, we have 4 different paths, and then we have an average cost, which is set about 50. And as you can see here, path number 3 is more expensive than the average. So in this case, the volume for path 3 will be reduced, and then that additional volume will then be assigned to all of these other paths, numbers 1, 2, and 4, which are cheaper than that kind of average cost. So here on the right, you can see what their volumes were for each of the paths before in blue. And so you'll see that path number 3 here, that volume gets decreased, and then that volume is going to get assigned to paths 1, 2, and 4. All right, so now we have our vehicles on the network. They are able to search for paths and choose their path. So now we have to take a look at defining different criteria to let the simulation know when that convergence has been reached. So this allows the user to define different criteria to just stop that DTA process automatically. There are a few different conditions you can set. The first one is the travel time on the paths as a whole. And then you can also look at travel time along the edges and volume on the edges. So over here on the right-hand side is where you can set up the number of the percentage of paths or edges that are required for convergence to be met. And then you can set the additional criteria here in kind of this first column. So for example, if we take a look at the travel time on path, this would mean that 95% of paths would have no change, and 15% wouldn't have a change in travel time. And kind of the same thing for the edges. And then you can also look at volume on edges based on the number of vehicles rather than a percentage. And this could be used if you maybe have a lot of OD pairs with really small volume, which might result in large differences in travel times. Say, for example, maybe sometimes a vehicle would make it through an intersection through a green light, maybe the next time it doesn't, and so it has a lot of additional delay. So this is just another option that you can look at rather than always looking at travel time. And then you can set the number of runs in a row that need to reach that convergence. And then once that has been reached, there'll be a little pop-up window that will tell you, and you can hit OK to end the simulation. All right, and then kind of our final option here is this route guidance. And so this is kind of looking at modeling vehicle decisions if they were using maybe like a GPS device. And so this will allow for vehicles to kind of reroute themselves while they're on their current trip. And so this will be set up, again, for the vehicle types themselves. So here in the equipment section, this is where you can choose 2 different route guidance options. And these can be set up with different strategies within the parameters window. So you can either have vehicles look for a different route to that destination parking lot, or you can also have them look for a different destination parking lot as long as it's within that same zone. And then you can also set up additional criteria for how often that new path search will occur, and also include an offset if you want to account for any delays that occur from sending information from that GPS device to the vehicles. All right, so I know that was a lot of information, but here we can go over just a quick example, just this little small test network. So in this case, we're having vehicles travel from zone 1 to zone 3. I've got 500 vehicles on the network, and as you can see here, they have some different wonky paths they can choose and decide upon to get to this final destination. So let me go ahead and pull up that model here. And so I haven't run this model at all yet. Up here in Traffic Dynamic Assignment and Parameters, I also haven't adjusted any of the parameters, so these will all be using the default values. And here you can see where we have these cost and path files set up. So these will just get saved to my directory. And right now I don't have anything saved, so none of those exist yet. So just to show you as well some of the paths that get generated, I'm just going to open up this path window. Since we don't have a path file yet, it has that little error. But you can see here we don't have any path. So I'll just press play and get some vehicles on the network. This runs pretty quickly because there's not much happening. But as you'll see, if you recall from the very first iteration, since there's no information about travel times on the path, vehicles are just going to use the shortest distance. So you'll notice here that every single vehicle is just going to take this kind of straightaway shortest distance path. And if I highlight that down here, you can just see that there. So let me run through this, and then I'll run a second iteration so you can see how some of those other paths get assigned. All right, so that's the first iteration done. And then you can see even here, we still have our first shortest distance path, but then as part of that path selection process, we have another path that's been found as another option for vehicles to take. So now you'll see vehicles will start to take this other option as they're traveling to zone 3. And if you select this attribute selection here, this will also allow you to see kind of what the volumes are looking like, so you can choose for each of the evaluation intervals that you've set, and you can look at the old volume, which will be the stored volume in that path file, and then also the new volume. So I'll just let this run through a little bit. And you can see here how we have kind of our new distribution of vehicles taking each of those paths. And then play it one more time, so then they found a third option for vehicles to take in order to get to that destination.